let's see if taking the transpose of a matrix does anything to its determinant. So a good place to start is just with the 2 by 2 scenario. So let's do the 2 by 2 scenario. So if I start with some matrix here, let me just take its determinant. So A, B, C, D, and then let me take its determinant. So this is going to be equal to AD minus BC. Now let me take the transpose of this and then take its determinant. So that would be the determinant of AC, the columns turn into the rows, and then BD, and the rows turn into the columns. And what is this going to be equal to? This is going to be equal to AD minus BC again. The only thing that happened is these two guys got swapped and they multiplied times each other anyway. So these two things are equivalent. So at least for the 2 by 2 case, the determinant of some matrix is equal to the determinant of the transpose of that matrix. Now that's just the 2 by 2 case. Now I'm going to make an inductive argument, or I guess I say an argument by induction. To show that this works for all n by n, for all cases. And the way you construct an argument by induction is you assume that it's true for the n by n case. Assume true for the n by n case. So let's assume, we assume that for n by n, that let's say I have some matrix. Let me say I have some matrix. Let me call it matrix B. Let's say it's an n by n matrix. We assume that the determinant of any matrix B, that's n by n, is equal to the determinant of B's transpose. That's where we start off with our inductive argument. And then we see if given that, is it also true? Is it true of n plus 1 by n plus 1 matrix? Because if we can say, look, given that it's true for the n by n case, it's going to be true for the n plus 1 by n plus 1 case, then we're done, because we know it's true for the base case, the 2 by 2 case, which you could say, well, that's your first n by n. So if it's true for the 2 by 2 case, then it'll be true for the 3 by 3 case, because that's just one increment. But then if it's true for the 3 by 3 case, it'll be true for the 4 by 4 case. But if it's true for the 4 by 4 case, it'll be true for the 5 by 5 case. And you just keep going up like that. So when you do a proof by induction, you prove a base case. And then you prove that if it's true for n, or in this case, an n by n determinant, if you can prove that given it's true for an n by n determinant, it's going to be true for an n plus 1 by n plus 1 determinant, or an n plus 1 by n plus 1 matrix, then you have completed your proof. So let's see if this is the case. So let me construct an n plus 1 by n plus 1 matrix. So let's say I have my matrix A, my favorite letter to use for matrices. I think the entire linear algebra's favorite letter to use for matrices. And let's say it's an n plus 1 by n plus 1 matrix. And just to simplify my notation, let's just say that m is equal to n plus 1. So we could call it an m by m matrix. And what is it going to look like? Let's draw its entries right here. So it's going to have, I'm going to draw more than the normal amount of entries. A11, this is our first row, A12, all the way to A1m. We have m columns, or actually n plus, which is the same thing as n plus 1. That's not n times 1 columns. This is n plus 1 as well. And then we do our second row right here. A21, A22, A23, all the way to A2m. Then you have your third row right here. A31, A32, A33, all the way to A3m. And then you go all the way down here. At the end, you have your mth row, which is, you could also say, is your n plus 1th row, which is A. So it's your mth row, first column. And then you have A sub m2, and then A sub m3, all the way to A sub mm. Fair enough. Now let me draw the transpose of A. So A transpose is also going to be an n plus 1 by n plus 1 matrix, which you could also write as an m by m matrix. I'm just going to have to take the transpose of this. Let's see, so the transpose of that, this row becomes a column, so it becomes A11. Then this entry right here is A12. It's this entry right there. Then you can go all the way down. You could have all the way down to A1m. Then this pink row becomes a pink column here. A21. You have I wanted to do it in pink. You have A21, A22, and you have an A23. And it goes all the way down to A2m. You have your green row right here. It's your third one. So it's A31, A32, A33, all the way down to A3m. And then we can just skip a bunch of rows in this case, but it's columns in this case. So you just draw some dots, and you have A, M1, A, M2. I'm just going down this guy, but this row is now going to become, which was the last row, is now going to become the last column. A, M3, all the way down to A, MM. And I have my transpose. Now, let's take the determinant of A. Let's take the determinant of A. Now, let me do it in purple. So the determinant of my matrix A, we could just go down this first row up here. It's going to be equal to A11 times the determinant of its submatrix. So it's the determinant of this submatrix right here. The determinant of that submatrix right there. We could call that the submatrix A sub 1, 1. We've seen this notation before. So it's the determinant of A sub 1, 1. And then it is minus A12 times the determinant of its submatrix. So you cross out that row and that column. And so that is going to be A sub 1, 2. And you're going to go all the way to, and I don't know what the sign on that is, so we could call it negative 1 to the 1 plus m. That'll give us the right sign for the checkerboard pattern, times the determinant of the submatrix for this guy. So we call it A1m, where you cross out that guy's row, that guy's column, and you're just left with all of this stuff over here. Fair enough. Now, let's look at the determinant of A transpose. The determinant of A transpose. We learned earlier you don't have to go down the first row, or you don't have to even go down a row. You could go down a column. So let me be clear. So for our determinant of A, we went down this row, and our submatrices, this was my first submatrix, my second submatrix. You know what it looks like. You would cross out the second column and that row, and whatever's left over would be the second submatrix, and so on and so forth. But for our determinant of A transpose, let's just go down this first column and get the submatrices like that. So this is going to be equal to, let's get our first term right here, A sub 1, 1 times the determinant of its submatrix. So what's the determinant of its submatrix? It's going to be its submatrix. You cross out its row and its column, and you're going to be left with this thing right here. Now, an interesting question is, how does this thing that I've just squared off, this guy's submatrix, relate to this guy's submatrix? Well, if you look at it carefully, this row from A22 to A2m has now become a column from A22 to A2m. This row, which is the next one, from A32 to A3m, has now become a column from A32 to A3m. If you keep going down, this last row has now become this column. So this guy's submatrix, or the determinant, or the thing we're going to have to take the determinant of right here, is equal to the transpose of this guy. So this is equal to A sub 1, 1, A sub 1, 1 transpose. A sub 1, 1 transpose. And if you go through it, and then we go minus this guy, minus A12 times the determinant of his submatrix. And if we cross out this guy's row and that guy's column, what is that going to look like? His submatrix is going to look like this. It's going to have that there, and it's going to have that right there. Now, how does that compare to A12? So A12 is if you crossed out this, and this, and you're left with all of this right here. All of this right here. So once again, you see that this row is the same thing as this column, that this row is the same thing as this column, that that row is the same thing as that column. So once again, the submatrix we have to take the determinant of is equal to the transpose of this thing over here. So it's equal to A1, 2 transpose. This thing, I could draw shaded in, is equal to the transpose of this thing, is equal to the transpose of that thing right there. So in general, each of these submatrices, when we go down this row, is equal to the transpose of each of these. So you keep going. So then you're going to go all the way to plus minus 1. We're going to go all the way down to the minus 1 plus m times the determinant of, it's going to be this guy, it's going to be this guy transpose. You can even do it. If you go all the way to, if you cross that guy out and that guy out, you're left with everything else on this matrix, and that's equal to the transpose of if you cross this guy out and that guy out. This row turns into that column, that row turns into that column. I think you see the point. I don't want to beat a dead horse. So that's going to be equal to A sub 1m transpose. Now, remember, going into this inductive proof, or proof by induction, I assumed that remember, this is an n plus 1 by n plus 1 matrix. But going into it, I assumed that for an n by n matrix, the determinant of B is equal to the determinant of B transpose. Well, these guys right here, these are n by n matrices, right? This guy right here is an n plus 1 by n plus 1 by n plus 1. Same thing for this guy right here. But these guys right here are n by n. N by n. So if we assume for the n by n case that the determinant of a matrix is equal to the determinant of a transpose, right? This is the determinant of a matrix. This is the determinant of its transpose. These two things have to be equal. So we can then say that the determinant of A transpose is equal to this term, A sub 1, 1, times this. But this is equal to this for the n by n case. Remember, we're doing the n plus 1 plus by n plus 1 case. But these submatrices are one dimension smaller in each direction. Has one less row and one less column. So these two things are equal. So instead of writing this, I can just write this. So times the determinant of A sub 1, 1. And then you keep going. Minus A sub 1, 2 times the determinant. Instead of writing this, I could write that because they're equal. Determinant A sub 1, 2 all the way to plus minus 1 to the 1 plus m times the determinant of this. These two things are equal. That is equal to that. That was our assumption in this inductive proof. A sub 1m. And then you see that, of course, this line, this blue line here, is equivalent to this blue line there. So we get that the determinant of A, which is an n plus 1 by n plus 1, so this is the n plus 1 by n plus 1 case, we get the determinant of A is equal to the determinant of A transpose. And we got this assuming that it is true. Let me write, assuming that it's true for n by n case. And then we're done. We've now proved that this is true in general because we've proven the base case. We've proven it for the 2 by 2 case. And then we show that if it's true for the n case, it's true for the n plus 1 case. So if it's true for the 2 case, it's going to be true for the 3 by 3 case. If it's true for the 3 by 3 case, it's true for the 4 by 4 case. So on and so forth. But the takeaway is pretty neat. You can take the transpose. The determinant doesn't change.